Yes. So there are two beautiful quotes from Nikola Tesla. So this says, if you only knew the magnificence of 3, 6, and 9, then you would have a key to the universe. The other side we have, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. So I'll come back to this, why I have written these quotes and why people might be wondering how this is important to this topic. Yes, let me just proceed. Now, the lines from Hanuman Chalisa, I would like to narrate it. Sukshma रूप धरि सिया ही दिखावे बिकट रूप धरि लंक जरावा. So when I was reading about this nanotechnologies, I felt it is just a sci-fi movie which I'm watching it. Then suddenly when I was listening to this Hanuman Chalisa, this line triggered me or was intriguing. See, Lord Hanuman, we all might be knowing the story about Lanka, where Sita was trying to, Hanumanji was trying to bring Sita out from Lanka. So in that case, no doubt, he had to destroy Lanka by putting it onto a fire. But before that, how did he enter? Now for that, he had to take a gigantic, size. That's fine. But in order to enter inside this Lanka, he had to take the tiniest form, which was usually not visible to human eyes. So maybe this is what is also intriguing other scientists, and this I felt we can correlate this line to our task. So now that we have been working from a room-size computers, and today we are talking about sensor networks where the size of the sensor node is about matchbox size. But we are not enough. We are not stopping our research at this point. We would like to see a sensor node, rather a tiny computer, which is solvable, that means which can be inside the body or which can penetrate into those locations where nowadays whatever traditional sensors we have, it's not possible for them to reach those places. And maybe let us see how exactly this started story in nano networking. Now, before I continue or begin my presentation, there are a few points. So I would like to thank, the various people who have represented their resources and made it available online in the form of either articles or in the form of research papers. So the credit goes to various authors and the owners of the materials who made them, where I'm trying to refer this presentation. But however, my contribution is the flow of the topics, that's the creativity. So now I have a number here 3, which relates to Tesla's point. Then next, for those who would like to explore, if you want to know from where I have to start, so these are the 6 papers which you can start reading, to get this starting point. So these 6 papers, and as you all know that in sensor networks, most often we try to hear the name Professor Ian F. Akildis, and the same person is the one, his team have started researching in this domain. That is about nano communications I'm talking about. We are not emphasizing on nanotechnology indeed, but nano communications. So these are those 6 papers. So now let us time travel to 2010, because that is the time where exactly first initial papers were started being available online after publishing. Now, this would be the flow of my content. How exactly nano communication started? So it all started just because we had something known as nanotechnology. So there will be a talking about in the introduction part. Then what are the manufacturing approaches? So those who are into manufacturing side or device development side, they can look at those aspects. Then coming to the architecture. So if somebody is working on the architecture layout, you can have a knowledge about that. Then finally we talk about the communication unit that exists, and then we slowly move on to the nano communications. Then we discuss about the various applications, then the architecture, and particularly it is a WNSN, wireless nano sensor network architecture. Then differences between WSN and WNSNs. And finally, the core topic of this presentation is what are the challenges in these electromagnetic nano networks. I'm emphasizing, please, most of my talk would be on towards electromagnetic side. So if you say towards, do you have any other alternative way? Yes, that we will be discussing. And then what's for today? And finally, the conclusion followed by the questionnaire session. So now, even I was curious to know what made people to think about the communication using nanoscale devices. I'll talk about what is nanoscale device later on. So it all started with the invention of graphene. So even the graphene part. So what people thought, like scientists, they knew one atom thick, two-dimensional crystal graphene existed. No one had worked out how to extract it from graphite. Fine, it was in the form of a crystal form from a graphite. Can we do it? So, and this was until it was isolated in 2004 by two famous researchers at the University of Manchester, and we should be aware of these two people by now. It's Professor Andrew Guillaume and Professor Kostya Novoselov. Now, this is the story that the stunning scientific feat came about and why these two people finally worked on it, and that led to a Nobel Prize in the year 2010. And these are those two people. So they started working for the first time about this graphene. Now please note that whenever we are talking about a nanoscale devices and all, it is not only restricted to graphene based products. There are also its derivatives and other versions which people are trying to use now. As I said, this is what it happened in 2010, and based on that availability of that nanotechnology product called as graphene, people have started developing various components. Yes, then after that what? So it all happened that Professor Ian Achilles when he was trying to interact with some of their students, the students started complaining. So we hear nanotechnology, we are hearing nano building, we hear something named as a nano tree. You believe me, people are also working on smart walls. Now smart walls in the sense, do you mean to say I can talk to walls in future? Yes. So recently I was just watching one Telugu television show in which a lady, she says that earlier we had people to share our sorrows or happiness or anything else, but nowadays it has become difficult. I share my problems with the walls. So maybe there are many such cases. So it's, again I repeat, it's not a fantasy. Yes, people are coming up with the walls which can help you in communication, and gradually, who knows, you may once try to talk to a wall, it starts responding to you. So then, just like how this Archimedes invented the concept of buoyancy, the same thing happened. Probably this happens with you and me also. All great ideas come to us only when you're in a washroom. The same thing happened while Professor Ian Achilles was having a shower. So all it suddenly clicked. Where I should start from? My students are talking about nanotechnology. So what is nanotechnology? It's triggered him. So he started referring papers which are related to microprocessor and its technology, from where it started and what was the current scenario. So this is what it happened. Then, so when he thought, if we have a processors, a microprocessor and so on, as per the Moore's law, the size keeps on decreasing. Then why can't we have nanoscale devices? And once we have those nanoscale devices, definitely we can have communication also. So this was the thought, it triggered him. But believe me, he says one of his talk, you can go through this video session here in his talk, where he says, and also most of the points are also picked up from that talk itself, where he has said that he is not a person from devices, nor a person from biology, nor a person from chemistry or physics. We are a communication people. So what should we do? So we need to start focusing on that. And then it started. So a set of scholars, they visited this professor seeking that they were interested in doing some in research in WSN domain. Then he said, you can stop that part. Please try to look at a new area that's known as nano networks or nano-sensor networks. And then the research started. Okay, just a minute. I'll try to put my earphones. Am I audible to you all?
Yes, audible. Audible.
Okay, if there is any external disturbance, please
some
let me know.
background noise were there. Yeah.
No, I think that is continuing. Let me just request them because this is an unexpected one. It happened. I don't know, they're outside. Still you get it, right?
Yes, yes. So some background noise was coming.
Okay, okay. Just let me.
Hard sound or.
No. Actually, there's a kind of a repair work going on. I guess this was an unexpected.
Dr. Manjula, you can
yes.
Again leave and again join.
Yeah. Thank you, ma'am. Thank you, ma'am.
Please try that.
Yeah. No, I'll just instruct those people. I'll request them and come back. Am I audible to you all?
Yes, ma'am.
Yeah, thank you. Yeah, fine. So that's what it slowly triggered the concept or the idea of nano communication. And believe me, it all started with molecular nanoscale communication, not the electromagnetic part, right? So, and these are the people who were the pioneers in the nanoscale communications. There's Professor Ian Achilles, and these two people, Brunetti and Blasque. Sorry, I did not get their images from internet sources, just only the paper. And one of their contributory paper is the first paper which I showed you in the beginning slide. Then we have Dr. Massimiliano Pirobon as well as Dr. Joseph Jornet. And these are the three people. On the left we have Professor Ryan Achilles, probably should be knowing. In the middle we have Pirobon, and on the right hand side we have Joseph Jornet. And right now we are doing a collaborative research work with Joseph Jornet, and most of the content which I have prepared, I have inspired from his thesis work and some of the contributory as well as the presentation. And the person who is in the middle, Pirobon, he has worked on molecular communication aspects. So if you want to know about the molecular communications, so I suggest you can refer to the papers from these two people. So you may explore more on, but as per my experience, these are the starting words. Now, you might be thinking, okay, just a minute. Probably I had not enabled this animation part here. I don't know, somehow I missed it. Yes. Now, in this case, you might be wondering that nanotechnology, is it happened only when graphene was invented? No, please. This started even before. Okay, I'm written in 4th century or even before that. And you can see that there are some images which I have taken it from internet sources. The colors which were used in those drawings were made out of nano-sized crystals or gold particles, I guess, but rather I can call it as, in general, nanoscale materials. So you might be wondering, like, why only those colors are there? Weren't there any bright colors or different shades? That's fine, that will be a secondary matter. So we'll discuss about some of the properties of nanoscale devices. And those properties, one of them will help you to get same device at a different size and shape will give you these colors. So it all started way back then. Now, after that later on, So exactly when this term nanotechnology came into existence is one person, maybe you can address him as a professor, Taniguchi. Okay, he coined this term. And what exactly was nanotechnology in his perspective? It was processing of separation, consolidation, and deformation of materials. Okay, fine. What are this processing, separation, consolidation, deformation? Maybe it's like twist, bend, tweak, or something, whatever you can call it as in an informal language of all these things. But this is happening at one atom scale or the maximum by one molecule. I repeat, it's one atom scale or one atom. You can play with atoms and this one. I'll also show you how one can play with the atoms and all. However, with perspective of the communication aspects, this is also like we can call this nanotechnology. It is enabling us to control the matter at the same thing it goes, atomic or molecular scale. But now, what is so special about nanoparticles, which is not seen in bulk materials? Bulk materials in the sense, the material which you find it, maybe you can take it as iron or something else, even the silicon which is seen nowadays in the latest technologies at present. Is there new properties? Now, again, this goes to back to physics, maybe chemistry and biology. And what are those? There are some new properties or unique properties which are not present, or you can say it's almost absent at the microscopic level and macroscopic level. So before knowing that, assume you know the properties. Then the question comes, we always, engineers, researchers, we try to see, can I exploit these properties? Can I borrow something from nature? So for example, a butterfly, it has very vibrant colors. Second, even it enjoys the rain, it never gets drenched. So what is that making a butterfly not to get wet? So can we borrow the concept from that and develop materials? So the same thing happens if you find there are some new properties of the graphene. Can we exploit them to make new devices? And once you get a new devices at the nanoscale, then we can start exploring new application domains. So then came the nanomaterials. So what does this nanomaterial consist of? We have some examples. Basically, it started with the graphene. It's again a carbon derivative. As we said, it's invention somewhere in 2008 or 4. It happened during that period. And from this, people developed nanotubes and nano ribbons. Now, what do you mean so special about these tubes or ribbons? Why the name? We can see it in the next slide. So graphene is a material where it's of one atom thick planar sheet. See, for example, even if you take a paper, there are certain sizes depending on the thickness. Now that thickness itself is visible to us, but here they are talking about a thin sheet, but it is of one atom in thickness. Okay, and then it is formed, the planar sheet is formed due to the construction of a honeycomb-like crystal. Maybe this is what is a concept usually borrowed even in a cellular structure, hexagonal cell shape. So these two are, what do you mean by this nanotube? You can take that sheet and fold it in the form of a tube. That's the name, you have it as a nanotube. Okay, I have swapped this one. And the ribbons, I'll just show it to you. So in the here you can see it as in the form of a sheet, and here you can see that in the form of a ribbon. Now, so if you would like to know, like we say that one can play with an atom. Is it possible? Let us have a look here.
And your screen is not moving up, so I think it has stuck.
Oh, you are not seeing this animation? What
No,
has happened?
no, we are not able to see it.
Okay, what you can see now?
Actually, your slides is on here.
Okay,
Nanotechnology
okay.
slide. I think you need to share that particular screen.
Okay, 1 second, let me just check. Okay, I was actually used with the Zoom. Oh, then this will not be in the background effects. Here it shows only that screen share is there. That's it. There is nothing. Any other options are not there.
Dr. Manjula, are you trying to
Yes, ma'am.
show any video?
Yes, yes, yes.
So you can unshare once and then start the video and then share.
Okay, 1 second. I think now. Oh, okay. Stop sharing. Yeah, I got it.
Yes,
More
yes,
actions.
yes.
Then is it okay? Just again, if I say open this share option.
Yes, just on the video, like video is video. You start the video, then you share
Okay.
while the
Okay,
video
okay.
is running in your background. You share the screen.
Sure, sure. Okay, let me just
Please
try
try
this.
that.
Is it visible now?
You have not shared yet.
So you need to share the screen.
Yes,
Yes.
yes.
Now
Yes.
you
Just
share.
Oh, those shared. No, it is shared actually.
But here it is not visible.
Okay. Okay.
No.
Anyhow, I'll share those links. Yeah, fine. No worries. I'll share those links. We can see later on. But let me just check. Now, is either my PPT are visible?
Yes.
Yes, yes.
Okay. Let me just go ahead with this. Okay, these links are there. You can just check how people have started developing a video, small video animation, which shows that a boy is playing with a single atom, but the boy itself himself is what is that? It's made up of atoms itself. So that was the animation about. Fine. Let us move ahead. Next, first, then comes why we should talk about these nanomaterials or devices at this scale. So nanomaterials have been analyzed in terms of electrical properties and optical properties in light of quantum mechanics. Because whenever we talk about anything new, we should see what are the characteristics and properties of those material and how we can make use of them. So at this scale, as I was already telling, they have some new properties which are not seen at the microscopic level, and these are high current capacity, high thermal conductivity. Of course, right now I am not exactly giving the numbers as it was just a survey part I was doing it. For numbers you can keep exploring. Extremely energy efficient, high mechanical strength, it's robust, highly sensitive, they are transparent. Now this high sensitive is what makes them a good candidate for sensor or the sensing devices we can call it as. And the list is still continuing. They have excellent chemical sensing also, or the magnetic optical properties and the behavior. This is the most fascinating point for people who would like to work in electromagnetic communication domain. Frequency and distance dependent behavior. Now you may say this frequency and distance dependent is not new. It is also existing maybe in the traditional communication also. But yes, please remember these two factors are dependent on, you can see that it depends on the colors at different size, shapes and the molecules. Now you may say how size of an object. Suppose if the size of the object is 1 atom, the behavior is different. If it is the size of a molecule, the behavior is different. Slightly if I try to increase, but not beyond the nanoscale range. But even then, they have different behavior. Shape also matters, and the presence of molecules. For example, in the medium, we always do the testing or analysis assuming an isotropic medium, and then we try to incorporate models considering losses into picture. But now here molecules, for example, presence of water or presence of oxygen or nitrogen might also influence your waves, electromagnetic waves. And this is not again just a story, we will look. So they are stronger in nature, lighter, more durable, with some modifications or something else, people are also trying to look into biodegradable or biocompatible devices. Water repellent, as I said, then anti-reflective, self-cleaning, and this is a concept which is used nowadays in creating clothes. Ultraviolet or infrared resistance, anti-fog, antimicrobial, and scratch resistance. Maybe there are many more. As you said, like you are unable to check the animation, but let me at least try to give one link from YouTube. Now this actually I have downloaded. No. There might be some ads or things. As I said, just I want to see if YouTube things are playing. This is one of the video which you can refer to. Yes. Now coming to the manufacturing approaches. So people who are trying to work in this domain, you can try these three ways. One is a top-down approach, the second one is a bottom-up approach, and the third one is the hybrid. Now the top-down approach is similar to you take a bulk material like the sculptor who is going to take a big large size stone and keeps to try carving out of it and make an beautiful idol out of that one. The same thing happens with the nano size top-down approach also. You take the materials, the downscaling techniques, microelectronics part or mechanical devices, and you keep on moving towards the atomic level. The second approach is you try to add a small quantity of these particles. Okay, and they also have this feature of self-assembly. So I'll just play a small animation. I don't know whether again it works or not. You will have the concept of what is meant by self-assembly. So either that approach we can follow, and the third one is an hybrid, where you are going to combine the features of these two. Now people, as I said, you can see here why mitochondria, DNA is coming here, antibodies, because I said we are still talking about nanotechnology, nano-communication. So when we say in general nano-communication, it includes both biological as well as non-biological, that is your electromagnetics. So whenever you see such words, these are the points which are related to molecular level. And please let me know if you are able to see again this video.
Which we get from one electron. You can just see the negative electrode connected to the wire.
Are you able to see the video?
We can only hear, ma'am.
Okay, fine. Let me just check.
Have you any link, ma'am? You can share in the chat.
Yes.
When you are sharing the screen, so while sharing the screen, just select the entire screen, not the window. Then maybe we can easily see all the videos.
Okay, just a minute. Let me stop this. Stop sharing. No, when I say option as sharing, it's by default taking one option.
For us, it shows two options, window and screen. So for all the options, you should the screen on.
Okay, and now here it shows enter full screen. That one option I'm having.
After you click on this screen, so there will be an option to show all the windows. So there will be two options just to scare this screen and all the windows. So I think you have to click on this window option.
Okay, and now this says exit full screen mode. Fine. Okay, include system audio. Okay, maybe that shares this. Let me just check. Now is my screen visible to you?
No, ma'am, not yet.
Okay.
It's not yet shared.
Ma'am, if you have any link, you can share in the chat box.
Yes, that would be fine. We will
try to show it. Okay, fine. Yeah, now is my slide visible to you all?
No,
Not
ma'am.
till now.
Not yet.
Oh, here it shows open. Okay, open share break. It's fine. Okay. Now.
Yes. Yes.
Okay. 1 second. Stop presenting. Presenting. Okay. Let me just move on. Okay, now these two approaches are present here. We can see that this is at the nature side, that is, as we are talking about the molecular communication aspect. The second one is the man-made approach. Now in this case, we can see that from millimeter, we talk about the microsensors. Of course, normal sensors is over. Now we are talking about the microsensors, where people from this VLSI domain, they might be aware of this word like MEMS, micro electromechanical systems, and then slowly we move on to this is a millimeter scale, and then we move on to micrometer scale, and then as we keep moving down, it stands for your nanometer scale. That means here it is 10 to the power of -3 meters, 10 to the power of -6 meters, and 10 to the power of -9 meters. So at both the levels, it is possible for us to deal with not only nature. We human beings are also trying to borrow the concept from nature and develop the devices. So if you want to go from top-down approaches, we know that we are scaling down, and currently we have reached up to this nanometer part here somewhere. I'll be showing in one of the slides that IBM has released a nanotechnology chip, which is of the 0.3 nanometers in size. So that means we are trying to move towards this end. The other way is you can start from individual atoms, keep on adding more and more atoms based on the requirement, and come up to the higher part. So this happens in the nature end, where I'll show you in one of the slides later on. DNAs, mitochondria, probably you might have been familiar with these terms like organelles and all. Like I remember I studied this when I was in class 6, where we draw the picture. Mitochondria is known as the powerhouse, and then it goes on. DNA is an entity in your human cell which stores the information, and it is this information that is being exploited now by the researchers to even send messages. And that DNA is in turn injected back into bacteria, and through conjugation process, the bacteria, they transmit information from one bacteria to another bacteria through this DNA, and the information finally gets delivered to the destination part. All right. When it comes to the design of these nano devices, there are two approaches. One is nanomaterial, as we said, like yes, both could be man-made itself. One will be talking about nanomaterial based devices, purely man-made, and biological nano devices. It can be two types, either man-made or it can be nature-based. So first, again, my emphasis would be on this one, nano-scale based devices or materials. So now we will look at the architecture of a nano-sensor node. How does it look like? Now, there's a picture. Now, you may say that the picture is so big. So what's a big deal in this term known as nano device? Please remember this is an enlarged, enlarged version of the nano devices. And you can see that all the basic entities which you find in a typical sensor node. We have a processor, we have a transceiver, transmitter and receiver, we have an embedded antenna, or maybe it's another version, people who are more into this, maybe it's a patch antenna. But I know like some of the term as like embedded antenna. We have an actuator. Suppose if I want to trigger some object or entity, I need to have an actuator. Then we have nanosensors which sense the phenomenon, like it can be temperature or light or the chemicals or anything else. And then we have this nano memory. In addition to that, they also have these batteries. Now batteries are not a traditional lithium batteries or a cadmium batteries. These are fine graphene crystals, okay, tubular structures. Now these are also capable of generating the power supply which is sufficient to power these devices. Now let us look at each of their functionalities. How are these devices different from traditional one? You can clearly see that the size of this entire devices, if you take all the three-dimensional, 6 micrometer, 2 micrometer and 1 micrometer. Now you may be worrying that you are talking about nanotechnology, you told about nano devices. Yes, These are the nano devices, nano processor, nanoscale processor, nano transceiver, nano antenna. So when you try to integrate all such nanoscale devices, obviously it leads to microscale entity, but still we call it as a nano sensor node. And please remember, this I'm talking in 2010, the idea was just conceived. Now if you have a doubt which company is producing this, I'll answer later on. Now people might be wondering how much is a nano, or what does nanos represent. So anything between 1 nanometer to 100 nanometer is your nanoscale. Now what does this stands for? It is 1 into 10 raised to minus 9. Now these components are based on nanoelectronics or nanophotonics, and further they include a graphene based nano antenna, and this particularly if I'll be talking about the work which was generated by Dr. Joseph Jornet. He has worked on this. Then we have also seen about nano transceivers, nano memories, nano processors, nano sensors and batteries. Okay, the whatever I had shown there. Now what should I call it as a machine and a device? See, these individual components are known as the devices, including these bristles. All of them put together we call it as a machine. That is the meaning of this statement here. And finally, when you try to integrate, it turns out to be, I said micrometer range. So how much is that? 10 to 100 square meters or a cubic meter also, because we have 3-dimensional. Then coming to how exactly integration is happening. We know about that VLSA part is one kind of where the fabrication techniques goes on. And this is in simple language, I will talk it as, they call it as DNA scaffolding. What is that? If you talk in terms of biology aspect, okay, now these are the complementary DNA sequences. This is one DNA sequence, this is also another DNA sequence. If you look at the beauty of this nature, the two DNA sequences, their arrangement of these, what we call it as the shapes here, is such that if I try to bring it close to this, it exactly gets filled in this gap. You can call this like one as a receiver, another part as a transmitting end. That is, if you try to fit them like this, it gets locked. And what are these blocks? These are adenine, guanine, thymine and cytosine. Now these are purely biological terms, but just I'm telling you in case if somebody is already focusing in this domain. So what they do is, coming to our carbon nanotubes, you have a base here, and you can see that connected to a silicon substrate. The base is silicon, fine. But over that, you are trying to put these nanotubes. Which are those? This is a nanotube and this is a nanotube. How do I fix this nanotube to the silicon? I need a gluing material, a gum, you can call it as. And that gum is nothing but your DNA kind of thing itself. So just to they apply appropriate glue and they try to fix it up. So this is one direction in which people are working. Then coming to the sensing unit. So what does a sensor does? It detects or measures events which are in the nanoscale. Now you may be worrying, I already have a sensor. I am working on an IoT project where my students have learned to detect the light or the temperature from a room. They collected the data and they have experimented, we got the result. So what's so special about these nano sensors? Please remember, in this case, our sensors, these nano sensors can detect even the concentrations which are as low as 1 part in a billion. It is as good as they can detect even, suppose if you are having around 1 million cubic elements, 1 million elements in that part, out of that, even if you have one compound from a different material, your sensor can detect that and report the information. So that is the strength with which these can sensors detect. Now, what are the different types of sensors that are available where people are expecting? At least we have we can put them under 3 classes: physical, chemical and biological. Now what can we use these physical nano sensors for? You can use them to measure the mass, pressure, force or displacement. And for all these things, what is the basic working principle? So the electronic properties of both the nanotubes and nanoribbons, these electronic properties, they change when these are bent or deformed. Now earlier I had shown you bristle kind of things, right? So in that bristle kinds of thing, maybe I'm having here, you can see that these are very tiny. Tiny in the sense, again, one atom thickness of this one, diameter is maybe like 1 nanometer, but this could be approximately 50 to 100 nanometers in height. Now when these are exposed to air or slight bend or pressure, they are going to generate voltage, and in turn that is used for application purpose to store the energy. So that's the concept used by this physical sensors. Now people are also trying to use this graphene based nanotubes to construct transistors, because we know that to store a memory device, what we talk it in semiconductor technology, where we use silicon and finally create field effect transistors. But now people are trying to use carbon nanotube based components. Now, what exactly is happening? Coming to electronics perspective, the on or off threshold of this FET depends on the dimensions of the tube, shape, and temperature, etc. So you might be worrying again, what is this? Always I'm talking about shape, maybe dimension. You can call it as a size also here. Yes, temperature. Maybe I'll have one video. Okay, I'll share that link in the chat box. You can have a look. Particularly, the local deformation of the tube creates a change in the on-off threshold voltage of the transistor. So we know that for the transistors, usually they don't. These are known as, I think we call them as active devices. In the sense, minimum amount of energy is required for them to start working. That's what we call it as a threshold voltage. And it basically, this is a principle which is used in nano-electromechanical systems, that is a NEMS system. Then coming to chemical nanosensors, these can measure chemical concentrations of a given gas, presence of a specific type of molecules or molecular composition of the substance. That's fine. Again, what are the principle behind working of these chemical sensors? As we mentioned now, the properties of carbon nanotubes and carbon nanoribbons, they change when we have different types of molecules are absorbed on them. In the sense, through research, maybe I have in the further slides, they say that the signal strength or the attenuation is impacted by the presence of molecules. If there's a water content, you have maybe some type of attenuation. If you have oxygen or carbon dioxide, you have different amount of attenuation and so on. Now, of course, you can either similar logic might also be applicable for these chemical based things. Now here in particular, if you try to put adsorbents, now it's not an adsorbent, it's an adsorbent. That means you give a thin kind of coating on this material to prevent its influence on the surrounding medium. So when we try to do this, there are two ways. Either it increases or decreases the number of electrons that are able to move freely through the carbon lattice. That means, is it not we are trying to have a control on the flow of electrons with this? Have you ever imagined that we can have a control on the electrons? Maybe, I do not know. But yes, it is possible now. Now, it is the moment you try to have a control over this, I think it affects on other parameters. For example, if you take the physical nanosensors, this same as that, even the chemical nanosensors, which are used in transistor configuration, presence of a specific type of molecules changes its on and off threshold voltage of the transistor. As I said, the threshold voltage is not fixed. Suppose if there is a water, threshold voltage level may be say V1, and I'll call that threshold voltage as V2 if there is an oxygen, where V1 is not equal to V2. And same thing goes with the biological nanosensors. I'll not stress more on this, but of course these are used to interact with biomolecular processes such as antibody or antigen interaction, DNA interaction, enzymatic interactions, and cellular communication. So out of these terms, at least something we can understand is the DNA part and the cellular communication. That means communication happens even through the smallest entity of a human being or any animal, that is a cell. So these are some of the constructions of these nano-scale sensors. You can see their sizes of this gap is 40 nanometer, and here is suspended your carbon nanotube. Again, it's a derivative of the graphene itself. Now here on the left we have drain, and then we have here on the right hand the source. Now this is CNT based, just a transistor. Now what happens when different types of external elements are exposed to this? Here it is a force, so it becomes a physical sensor. Here we are exposing it to a gas, then we can talk this as a chemical sensor. Then input given is antibody or antigen, then we can call it as a biological nanosensor. Here you can see that there are some Y shape of devices. I think these are as per biological terms known as ligands or the receptors. So they try to attract these antibodies or antigens, and accordingly their behavior keeps on changing. Now we have seen this is a nano sensor. Let's talk about this actuation unit, or also known as the actuator. What does this actuator's job do? Say for example, I'm talking in terms of regular sensor networks. Our task is you're trying to control the AC with the help of a sensor network. If the room temperature falls below the certain temperature value, you want to turn on the AC. But once you feel that now the room temperature is cool enough, or okay, I want to switch off my AC, then your sensor will accordingly detect the temperature, and if it is more below that temperature, it is going to give a command to the AC to turn it off. Same thing happens with the nano sensor devices. You believe me? Nowadays people are trying to, it's already there I think, tiny robots which are injected into your body, and their concept is borrowed again from one of the agent itself. I'll show you in a couple of slides. So in how these sensors are acting as an actuators in case of medical domain, they try to put a drug in each of these robot devices, and these robots, they go to a particular target. Suppose if I have a wound here, or maybe there's a cancer area, prone area at this point, so then that particular nano sensor device is made to flow up to that particular point, and then it starts showing its effect. So they're also equipped with tiny sensors, cameras also, or we can also call this another term as targeted drug delivery. So once that nano sensor reaches the particular spot, then it releases the drug. So then the drug starts acting on your body. That's the job of your actuation unit. But I'm talking in terms of biological sense. What happens in terms of electromagnetic sense? So we have physical nano actuator, and the principle on which these devices work is on electromagnetic wave, where it can bend a nanotube or the current. Fine. So what happens if it is bent? Based on this principle, that means you keep a nanotube like this and pass electromagnetic signals through this or over through this one. Then what happens? That device slightly it bends. So when this is happening, people are expecting it that device to act as a tweezers now. You know that tweezer is a kind of a two-handed device which is used to remove tiny elements. Maybe if a thorn is pricked to your hand or somewhere else, you try to use these tweezers and remove it. So these nano tweezers, they can be closed by applying a specific voltage and then open. So for closing you need a voltage, but by opening you need some external macro actuators. Now you may be wondering, what should I do with this nano sized tweezers? People are trying to use them in medical applications. For example, just like I have discussed about the physical, we also have this chemical and biological. Based on the interaction between nanomaterials and the particles, electromagnetic fields and heat. Okay, this is a basic principle. Now, for example, people have developed nano heaters. Okay, now again you may say heaters. You have room heaters at home, fine. Now, what else we need? I need a heater which is tiny in size, very small size. So you may be wondering, what should I do with this, such a small size of a heater? Now, you can inject such particles into your body, as I said, and selectively damage or kill the cancer cells. How? By heating them. So this is one beauty of your nanoscale heaters. Then magnetic nanoparticles and gold nanoshells. Okay, these can also be used in targeted drug delivery. This is what I was talking about. The next, power unit. So nanomaterials, we can also use them to create nano-scale devices, the nano batteries. So what's so special about these batteries? Very high power density, reasonable lifetime, and charging and discharging rates are appreciable. However, the self-powered nano batteries are introduced that convert, yes, again we have different kinds of, because you might be wondering at what interval I have to charge and discharge them. Should I keep it to a power supply and charge them and then put it into the target area? No, we are expecting them to have energy harvesting equipment, and that in turn will charge your batteries. So can I say I can have a perpetual network? Yes, it is possible. So mechanical energy or vibrational energy or the hydraulic energy is used to produce, extract the energy from all such physical phenomenon. So coming to the power unit, these nano batteries have very high power density, reasonable life. Okay, I think it's done. Yeah. Now there may be, earlier people were talking about lithium. I've just seen recently people have come up with graphene based nano batteries. Now what they say is the traditional lithium batteries, if you take, okay, you have that battery with you, just try to put a nail on it and hammer it. The heat which is generated due to the hammering part is passed on to that battery, and then it's that small amount of heat is enough to burst that entire battery. And think that these are the batteries which are nowadays fit in your vehicles also. So now people have experimented, if you are using a graphene based nano batteries, even though there is a heat, it is going to disconnect that battery system and put the entire things into off mode, more or less. So that is one advantage of having your nano batteries or graphene based batteries. And the capacity of this one is 45 microamp per hour per centimeter square and per micrometer. So as I was telling, we need self-powered batteries because you want to harvest energy from that. And for that, what people have come up with, zinc oxide based nanowires. As I said, it's not only the graphene, but nano-scale devices can be developed from different materials or sources. So people are talking about zinc oxide based nanowires. Okay, these are used to produce piezoelectric effect. So you should be knowing from your basic electronics, this piezoelectric effect will help us in generating the voltage when subject to bend. That is what I was talking about earlier. And then you are trying to run your systems. So further moving step one ahead, you need to have oscillators. Now these oscillators can be used to harvest energy from the wide spectrum of the vibrations. As we said, mechanical vibration or the physical vibration or the aquatic vibration, and the component which is helping us to do this is your oscillator. Now this energy can be directly used by the nano device, or also you can use it to charge a nano battery. Again, there is no any further conversion required. Now it was envisioned that energy could be harvested from electromagnetic waves. This is good, because nowadays we find electromagnetic waves everywhere around us. Can we try to exploit something from the nature, space? Yes. For example, a resonator based on NEMS, it can be used to convert electromagnetic radiation into vibrational energy. So when you do this, further that can be converted into electricity. You have it here. So electromagnetic radiation is incidented onto a NEMS resonator, which starts resonating or creating vibrations. I'm repeating, it creates vibrations, and this vibration is given as an input to a zinc nanowire, and that further is going to generate the energy. So why can't we harvest this energy and keep our device active forever? Now we have seen sensors, actuators, as well as energy device. So now the heart of, should we call it as a heart? Yes, maybe brain, processor. The processing unit, again, Nanoscale processors are possible with the help of field effect transistors. Again, graphene can also be used here to build this FETs. Now you might be wondering why graphene. Why my emphasis is on graphene. These are not only smaller but faster. Then their ballistic report shows they can travel at a longer distances without even being scattered. So for example, when we are telling that electron movement is necessary for us in any of the application, once you try to project it to travel for a certain distance, then it has to travel up to that point without even getting deviated from the normal path. So this property, it makes them used in the deployment of fast switching devices. Then another feature is the reduction of channel length that contributes to faster response of the transistor. So those who have into VLSI part, they might be aware of the channel between the source and the drain part. So that channel, earlier slides I showed it is just around 40 nanometers in length. So people are trying to reduce that so that you can have a faster transistor response. And theoretically, it was proved that the switching speed is up to hundreds of terahertz. Now 100 is fine, tera in the sense 10 to the power of 12. 100 into 10 raised to 12 hertz, that is the frequency with which these devices are operating. So some of the examples I'll try to directly quote here. I'm not talking about the manufacturing technologies, some of the examples. First, world's smallest transistor, say around 2008, it was maybe developed, and it was based on a thin strip of graphene. And just one atom, that means one row, it consists of 10 atoms, approximately 1 nanometer thick transistor. So you can see that in this reference. Up to 2011, the technology that was available was 32 nanometer size devices. So that means your processor, you can call it as a transistor. In 2011, approximately somewhere during that period, 20 nanometer transistors, they were already coming to the market. But however, okay, in 2014, DARPA has created the first 1 terahertz computer chip. That means it was almost tested in the lab. Please remember 1 terahertz, I'm taking is 10 to the power of 12. Okay. So later on I'll share the slides. You can just go through this link. Some are taking to the HTML pages and some are with the YouTube links. Now, as of 2018, smallest computer in the world, okay, and that which can fit on the size of a grain. This was developed by Michigan University, or University of Michigan, sorry, I should be pronouncing it correctly. You can see this is a rice grain, and here you find it a nanoscale processor. Now, what are its features? The size of this computer, it's 1 into 1 millimeter, 1 by 1. So this side it is 1 and this side it's 1. It is designed to be a precision temperature sensor. Now this can detect only one phenomenon at present. It can detect temperature and can report this temperature in clusters of cells. Yes, okay, fine. Now cells might be they're talking about this in biological sensor which can be sent inside the human body, and it gives you a temperature with an error of 0.1 degree Celsius. Now, for example, it can measure the temperature of tumors and conduct their cancer studies. As I said, these are biological one, man-made but biocompatible. They can also be used to monitor oil reservoirs, conduct audio and visual surveillance, and maybe there's some other experiments. However, in 2019, it was a milestone kind of thing for us, like in a carbon nanotube, microchip sends first message. And as usual, we programmers know the first programming language we learn is printing the message hello world. So what does this consist of? A tiny tubes which replaces silicon transistors and may lead to much faster energy efficient microchips. Now this is a 16-bit processor. You may say, madam, when my computer is working, or maybe I have a sensor node which can have more than this, why we need to go for 16? Please remember, this is of nano-scale device. Then it has 14,000 transistors, making it the largest of its size to date. So So when all these were put together and people were able to really send a message, this one, hello world, I am, and this is the name of that particular nano computer or nanoscale device. But as on to this date, but probably May, it's 2021, IBM has released its world's first 2 nanometer chip technology. Okay, and this is based on nanosheet technology. Okay, it's not maybe a derivative again of or a version of graphene based. And what's so special about this? It has 50 billion transistors just on the chip whose size is of your fingernail. That means within this region you can incorporate 50 billion transistors. And think about how much information you can store in a that particular size of chip. So another thing which we need to talk about is your memories. Quickly I'll run through. So it all started with Richard Feynman's observation that he said that we can store 1 bit in 1 atom, but in order to avoid interferences and all, he proposed a model consisting of 5 by 5 matrix, that is 25 atoms to store 1 bit of information. So if you try to really implement this one, okay, we'll have 1 gigabits of information that you can store it in 1 micrometer cube of element. And elements that are used are gold nanomemories and magnetic nanomemories. And please remember, when I'm talking about this nanomemory, I was giving a seminar presentation during my final year graduation in the year 2002 for this program, final year seminar presentation. My topic was on protein memories. Sorry, it's not that. There's a bacteria known as rhodopsin. Its life cycle is utilized to generate the information and store it. So now, except that word rhodopsin, nothing is clear in my mind. I even tried to search those materials because way back then there was no means to even store our files and all. So, but still it is, this is, I was thinking it's a fiction, but not a fiction. Yeah, now people are moving towards integration of 3D devices. Fine. I think it's just now in 2020. Yes, maybe it's slightly back we are going. So here they say that this 1 atom memory unit. Earlier I was talking about the processor. Now we are talking about the memory unit. So what is so special about this? They try to build up this in terms of a mem resistor, which has a capacity of about 25 terabits per square centimeter. 25 into 10 to the power of 12 bits you can have in 1 square centimeter. That means 100 times higher memory density than the commercially available flash memory devices. Now, coming to slowly we'll move on to the nano communication and networking aspects. This picture shows that there's a broad domain where I would keep working, me and my team, but focus is more on to networking part. Okay. So we'll just start with the nano communication unit. Now this is a typical block diagram. You see it in any communication system, whether it's a macro, micro or a nano. We have encoder followed by a transmitter, then we have channel, then we have receiver, and then we have a decoder. Now enabling communications among nano machines is possible with the development of. So when we say the communication is possible, that two entities are required for us apart from processing, sensing, everything. One is the antenna, the other one is transmitter and receiver. If you can do these 2 devices, fabricate them at nanoscale entity, yes, it is possible. Now 2 implementation approaches are identified for nano antennas. One is electromagnetic based nano antennas. The other approach is optical based nano antenna. Now both the approaches were, I think, looked at and dealt in detail by Joseph Jornet and his team. So you can see his contributory work from this, and maybe you can refer to his thesis if you want to know more about these details. Frequency of operation of all these devices is usually in 0.1 to 10 terahertz. Now people at the beginning, HOD sir was telling that in future your 6G or 5G or 6G, maybe in future we have 7G, we try to use, but of course it's not the nanoscale devices, but it is the frequency band in which we try to explore. That is a terahertz band. So again, there are two ways to look at. Working in terahertz band is totally different aspect. Making use of this same terahertz band, but working for nanoscale devices is another aspect. So when I talk about nanoscale communication, it is a communication which is happening within 1 meter. I repeat, nanoscale communication means the distance between sender and receiver is at most 1. The moment you cross 1 or more, slowly we go into micro scale range. Then if I say, if you have a question, can we use same nanoscale but at a multi-hop acting as a relay and cover a little bit larger area? Yes, that is possible. Now, next question comes with the scalability. What should be the maximum area? So those things are yet to be explored. Now, can we just reduce the dimensions of the classical antenna? Say for example, upper limit I will take for the term 100 nanometers. Before answering this, you just try to look at, if your height of the antenna is just 1 nanometer, this much should be the frequency of the signal. And if your height of the antenna is 100 nanometers, and it should be 7.5 into 10 raised to 14 should be the frequency of the signal. So definitely your this one, what is it, traditional antennas, can I have such a high frequencies? You do have high frequency signals, but I cannot use all those devices and equipments because they are not meant to work at such high frequencies. Therefore, the answer is no. Then how do we do with this? Nano networks. But what we can, but we need some materials like nanomaterials. Nano antennas. As we said, graphene is the one element which is used to build these nano-sized antennas. So what are some of the unique properties or observations that were made? We need to understand that the wave velocity here, the electromagnetic wave, its velocity, when it is traveling through these carbon nanotubes or ribbons, it is 100 times less than the speed of light. So we know that the speed of light in vacuum is 3 into 10 raised to 8 meters per second. But however, its value reduces by 100 times. Now, so if you start playing with frequency, vibration and energy, then digging more into the relationship, you will understand that deviation or reduction in frequency or increase in frequency will have impact on resonance frequency also. So the reason for this 100 times less than the regular speed of light is due to two factors. One is structure of the object, temperature, surrounding temperature, as well as the Fermi energy. Now this again boils down to physics, your conduction band, valence band and the Fermi energy and all. So as a result of what I said earlier, resonant frequency varies. Now how much is it, increasing or decreasing? So the resonant frequency is 2 orders of magnitude less in your nano antennas compared to traditional antenna. So the moment your resonant frequency changes, all other parameters are also affected. So therefore, we need to be very careful while studying, making the analysis. So another aspect is the radiation efficiency. What is this? It's a ratio of the radiated power to the incident power. Suppose if I give an antenna 10 units of energy to it, is it going to radiate 10 or 9 or 8 or 6 or just 2? So that is what we need to talk about, this radiation efficiency. Now, this can be impaired. That means it might get reduced because of the quantum phenomena. You might be wondering, like always I'm talking, what is this, why it is affecting and all. See, when you're talking at the atomic level, size of the object is at atom level, and when you try to put it in any media, whether it's an electromagnetic radiation or biological system or components, the size, the dimension of this device is so small that the surrounding phenomena is having a higher impact on that. So that is what much it talks about. I'm just giving a brief idea on this quantum phenomena. So you might Till now, we all are curious to know what are the research challenges. That's what was the title talking about. So for the nano antennas, what we required, you need accurate models for nano antennas. And where nano antenna means, again, we are talking about carbon nanotubes and carbon nanoribbons. Now, if you are finding new type of nanoscale antennas are developed other than this graphene tubes and ribbons, yes, there also you can try, but one is a model. Second, so this entails for providing a details on specific band of operation. Now, when you see in which band these antennas are made to work, if I tell a traditional sensor networks, quickly you will tell it works around 2.4 gigahertz of frequency and allocated spectrum. Now, in this case, nano antenna designs and radiating nanostructures need to be developed by exploiting the new properties of the nanomaterials. So, for everything, there is an interdependency, frequency, behavior of the object at the different frequencies, that is your resonant frequency, and the moleculars or the surrounding medium. Now, develop nano antennas that can efficiently resonate at different frequencies within the terahertz band. And new antenna theory must be defined by taking into account different quantum effects which are observed at nanoscale. So what is not seen at a regular microscale environment, you see them at the nanoscale behavior. Then we'll talk about the antenna part is done. Now is the transmitter and receiving equipment. So what is such a tiny device, what it can do? It can do the following tasks. What are those? Baseband processing, frequency conversion, filtering, power amplification. Yes, what else? I think this is sufficient for us to have transmission and the reception of information. Now these transceivers, they operate in 1 to 10 terahertz band, and these are possible using radio frequency FETs. So in 2010, IBM had demonstrated graphene based RF transistor. Yes, it was possible way back 2010 itself, which started switching at 10 gigahertz frequencies. So 10 gigahertz, but we are focusing on terahertz. That is the first range of the terahertz starts at 1. Yes, their target was 1 terahertz. Maybe they have developed, I think we have, maybe somebody has developed. These are the papers which talk about, if you want to know more about multipliers, we have this paper on graphene frequency multipliers. And then if you would like to know more about graphene based oscillators, which can generate at 1 terahertz frequencies, we have this paper on high frequency devices based on graphene. Then a single nano, carbon tube based transceiver have also been proposed. Just one nanotube, okay? With that, they are telling transmitter and receiver is possible. Now, don't think that it can deal with very huge processing power and all. No, they can deal with the phenomena which is at nanoscale itself. Electromagnetic nano transceivers or nano radio. These are able to modulate and demodulate an electromagnetic wave by means of mechanical resonance. So that means in simple I can tell we also have a transceiver with just a single carbon nanotube. However, this approach requires very high nanoscale power sources for active transmission. Now the power sources should be defined separately or designed separately for such type of transceivers. Then it is necessary to characterize and model the electronic noise which is present in the graphene. Why? Because noise has a stronger impact on signal to noise ratio. Yes, those who are working in the communication side, they also know about this. But only thing is the frequency range in which you are going to operate is what matters. Now this in turn limits the communication range of the devices. So therefore, I think its point comes here. Graphene shows for larger lengths. Yeah, why people are choosing graphene means it shows that almost ballistic transport of electrons for longer lengths, maybe up to 1 meter also. That is, thermal noise created by inelastic scattering of electrons in the materials is very low. Thermal noise is very low. Now, therefore, new communication and information modulation techniques have to be developed. So, these are some of the research challenges which one can explore while developing the communication units. Now, come to this is the narrower part of the under broad topic. Still it is a communication, but we are focusing on networking aspect. So what is possible here, or what is existing actually? Ultra broadband communications in nano networks. Terahertz band, it spans over, okay, frequency bandwidth is already mentioned to you. Now, is it possible to have communication at these frequencies? Because those who know that relation between height of the antenna h, frequency of operation f, or the wavelength, then definitely their mind starts thinking, to work at these frequencies, my antenna has to be very gigantic in nature. How to do with this? So he said, if yes, do we have such devices to operate? Yes, it is possible. So it is demonstrated in this work by Dr. Joseph in his research work that a 1 micrometer long graphene based nano antenna, it resonates in this band. So right now, for communication purpose, we already have graphene antennas. So people who want to set up a lab, we can request him and see if those are already available at the market level, or maybe at least at the institute level or an organization level, we can order and bring it them and test it. So that's a good news. Fine. What next? We need nano transceivers, we need new modulation schemes, and we need new encoding schemes. So it's not that just I have an antenna, I have there's a transmitter and receiver. No, we further need to have some of the techniques, modulation techniques, encoding techniques, decoding techniques and all, which are matching to these. That means all should be lightweight in nature. Some people might have already thought in your back end, I can try to do what knowledge we have gained in WSN part or something else, same thing I'll apply here and do it. No, Professor and Achilles himself was saying in that talk that please don't try to use existing one, make fit into nano networks. No, their behavior is totally different. Try to exploit those properties, then you will see the beauty. So I'll have another 15 minutes. So what I'll do, just I'll talk about the possibilities where you can see, as I said, the communication distance can be just 1 meter or so. And if you would like to know the beginning of the new modulation schemes which are developed for these are femtosecond, 100 femtosecond long pulse. We know that pulse based communication systems are available, that is pulse modulation kind of things. Same thing, on off technique, but what's special in this is just the pulse duration is varied. Now, not only that, that in turn again depends on the channel conditions and all. So if you would like to know more on this, you can refer this paper, channel modeling, the first paper, and for the modulation scheme, the second one. Okay, now quickly let us see a few applications. I'll show you two broad things. So one is inside body network. People might have studied about body area sensor network, where sensors are deployed outside the human body, maybe on the hand or the wrist or on the head. People collect the signals and send the data to the researcher for further purpose. But now you can see that these sensors are deployed inside the human body. So this is the setup which is used to measure the condition of the heart. This is the setup that is used to measure the condition of your digestive system, followed by the intestinal system. And this is for your brain system, brain condition analysis. So here in this thing you can find tiny entities are known as the nano-scale sensors. And this triangular form one is the nano-scale controller or nano-controller. And this part we all call it as your nano-link. Now, all these are interconnected to a device that is known as a nano-micro interface. That means this particular device should have the language of nano networks as well as the traditional macro networks. So that is the meaning of your nano-micro interface. From this, now this entire part alone will constitute your WNSN, wireless nano-sensor networks. The moment you try to connect it to internet via those respective gadgets, like for example, this is called as a gateway, and through internet you are sending the data to an medical officers, then it forms an internet of nano things. Now these are various applications in environmental monitoring, plant disease monitoring, and this is your smart office. Nowadays, due to COVID, we all are trying to ensure that often we wash our hands, we sanitize them, make sure that we maintain some physical distances so that these molecules, tiny molecules, don't know where they get settled and all. In future, if you try to deploy them, okay, these will continuously sense even those molecules, that is COVID virus molecules will be sensed, and that information will be sent to your mobile app telling that this place is contaminated with COVID virus. Please be careful with that, and then you take necessary action. And this is a combined model, actually, the network model. Further applications where Professor Sir was asking us to explore is this terahertz band communication. So you can use in real life for your personal area networks, maybe between your CPU and to your laptop, or maybe you have some other device you want to share it. For example, just like Bluetooth, but the difference is usually the amount of data rate. Then you can also use them in wireless access networks. So all these images I've taken it from that same YouTube session. The reason was these were the pioneering works which we are trying to carry our work, research work. And also you can have terabits wireless networks. Then you can also use them in military purpose. So there's a combine. And we are talking about the nano network architecture. I have briefly explained about the architecture part. What does it consist of? It has nano sensors, nano routers, and nano micro interface devices and gateways. Now coming to what are the challenges that one faces here. So this is the band. If people are looking at where exactly this fits into your electromagnetic spectrum, this is the band which was unutilized till date. But however, please remember, terahertz frequency signals were being observed or monitored by US Defense when they were dealing with satellite signals or something else. But then what is so special now? We are trying to explore more in the domain and study their possibilities of sending and receiving the information. Yeah, in this case, what are the challenges? See, you have 0.1 to 10 terahertz, but I kept on telling that the peculiarities include molecular absorption, okay, and what happens to these molecular absorptions is, let me just show it to you. There are two types. We talk about the spreading loss as well as the molecular absorption loss. So I'll show it with respect to this figure. Now, this is the frequency range. As they kept on increasing the frequency in terahertz from 1 terahertz to 10 terahertz, and they tried to vary the distance between the transmitting device and the receiving device. Now you can see that when the distance between the two communicating entities is 10 micrometers up to 10 millimeters. Okay, fine. Till here, that means in this range, there is no loss at all. That means entire frequency band, that means 1 terahertz up to 10 terahertz is available for us. But as the distance between those two communicating devices increases beyond 1 meter and up to 10 meters, it was tested using those graphene based antennas. People found that you cannot use this entire spectrum to, there are losses that are coming into picture due to these two, spreading loss as well as the molecular absorption losses. So as a result, what happens? You see that there are sudden spikes here. So this indicates you cannot get a single entire window of 10 terahertz at a stretch. What they have observed is chunks or blocks of frequencies are available for the users for longer distances. So right now our focus is for very small distance itself. As we said, we are moving towards network layer issues and all. So it's the same thing I have explained here. Then you can see that the presence of molecular noise. What is that molecular noise and all? Like if there is a water content, then what happens? If there is oxygen, if different amount of water is present, how that is going to affect the quality of the signal? That is what was studied. And this picture shows about the noise temperature. Because if there is a surrounding temperature due to any of the surrounding environments, that creates internal noise. So how much is that noise, to what distance it is affecting, and for what frequencies it varies on the distance. So it is again observed the same thing. For lower distances it is almost zero. After that you find it several peaks of attenuations are seen. Okay, now people sometimes we see about or listen to, I know every cell of you, maybe it's a kind of conversation, informal conversation that we usually have. When you say I know everything about that person, then how does that matter with the sensor network, nano-sensor networks? So people have envisioned that the amount of information that nanosensors may require is potentially very large. How much large is what? It can give you the information even from a single molecule that is present in the atmosphere. That is the amount which you are going to get. Large bandwidth will allow efficient and simple multiple access schemes, that is a media access schemes, people who would like to explore. I'll talk more about in a couple of seconds. So I think these are the common problems which we find when we are dealing with communication aspects. What is it? Line of sight communication as well as multipath signal communications. Now in this case we need to be careful that always I have been telling that shape, size of the object also matters. That is going to have influence on the signal frequency and attenuation part. So there are some common materials found in the office, even the human skin, and these all have negligible roughness. Even the skin is not so smooth. There are certain pores and all. For us that is okay, smooth, but for these nanoscale devices that roughness it will definitely matter. It is just like a bumpy roads which we often find them during our journeys on roadsides. So we need what is the new research that is possible? Try to develop new fairing models. And what about this particle scattering? See, the signal is three types of effects. One is the signal gets transmitted, some of them gets reflected exactly back. The other one is they get reflected at a different angle. That's what we see it as a scattering phenomenon. Why does this matter? See, the diameter of a water vapor is around 0.28 nanometer. Now this is more than 5 orders of magnitude below the wavelength of the signal, which is traveling in a terahertz frequency range. Now if that is the case, obviously we feel that tiny devices are also acting as obstacles for us. Not these buildings and all, even the molecules are also acting as obstacles. Okay, scattering, you have to just consider this effect of the scattering, which is defined by as a relay scattering. You need more models to understand this phenomena. Till date means when? Till 2010 there were no research models existing in that direction. If you say what about now, yes, these are possible. And we also have people have already worked under these encoding and modulation techniques. To know more about that, in view of time, I'm just running a bit fast. So these papers are already given to you. You can have a reference with them. I would just like to show my concern in this. So for example, when you develop either MAC layer protocols or network layer protocols or transport layer protocols, ultimately we can start working on the cross layer approach, where we need to think about the parameters such as energy of the pulse, how much energy should be there in that pulse modulation techniques, how many pulses should be there in one single burst, what's the time difference between two consecutive pulses. So all these we need to take care of when you're going for cross layer form of optimization. Now, this is that 100 femtoseconds long, or also known as 1 picoseconds pulse based communication. Do you find pulses here? If yes, I'm happy. So these are those pulses. And the distance between these pulses is very high, around 50 picoseconds. Now this type of, this is again known as in general on and off mode of communication part. But to understand the beauty of that, I suggest you to read Jonat's paper on modulation technique. And further research issues that exist in this domain are, one of them is synchronization, but still you find many more. So if you read this paper under this topic, sensing aware information routing, we need to understand that the properties of the physical channel, power and bandwidth, and exploit their interdependencies between different layers in the protocol stack. There are many more ingredients that we need to take care of while designing wireless sensor networks. So for that, what we have to do is characterization or characteristics of nano devices that influence the communication in this are both either nano ribbons or nanotubes all have their atoms exposed to medium. And this makes them very good candidates for sensing application. Fine. But at the same time, nano antennas are also made of graphene material, right? That means, will they work properly, or the presence of these molecules will have effect on their radiation efficiency? Yes, through research they have observed that presence of molecules and absence of molecules have effect on the resonant frequency of the antenna. Then what is the solution? One solution is to coat these antennas with absorbates. But however, if you do that, your antenna will work properly only if those molecules are present. If those molecules are absent, considering that for which you have given a coating protection, their efficiency becomes low. So it's like a trade-off. We do not know what type of molecules are present in nature. So one solution which they suggest is, why can't we exploit those characteristics and generate new kind of modulation techniques? So that's what we talk about. Try to use those characteristics and develop new solutions for modulating and demodulating. Okay, now these are some of the differences between WSN and wireless nanosensor networks. People might be interested to know. I'll just tell the differences. Now in WSN, hundreds of sensor nodes for a typical application, whereas for an WNSN we need thousands of nanosensors per millimeter cube. Then here the sensor node is of the size of a matchbox, whereas the size is of around 10 micro square meters. And these are deployed usually outside the human body, if I take one example, to collect some of the physiological parameters, whereas nanosensor nodes are deployed or soluble. Yes, you can take them in the form of a medicine also. Then frequency band of operation is different. Of course, they work in 2.4 gigahertz ISM band WSNs, and WNSNs works in terahertz band. And the typical data rates include 250 kilobits per second, whereas in WSN for nanosensor networks it is about terabits per second. Till now I was talking about only nanomaterial based nano devices. However, we also have biological nano devices. What are those? I was talking initially. This is for the people who are working in molecular domain. Just 2 or 3 slides are there. This is a cell which is present inside our body. Each part of the cell is compared to the component in your IT device. What is that? Nucleus. Nucleus is mapped to a memory. Mitochondria is acting as a powerhouse, as a battery part. Then DNA will be mapped to a control processor. It goes on. So other devices are also mapped to this. And sometimes you also have a flagella called as pilla or cilia. This helps this cell to move. Now in our case, we need to incorporate mobility to our device. This is a clear picture from that talk which I have taken. Now this was the device I was talking you. This a bacteria based communication is also possible. Based on this, people have also developed a tiny robot which has a camera, it has a payload and also such type of flagella. So these tiny robots, they enter inside our body, and through the camera, the robot will be sensing the normal cells and the cancer cells. The moment this nano robot reaches the cancerous cell, that payload will be triggered. So what does the payload consist of? It consists of your medicine. So that is going to be injected into the cell and that is going to kill it. See, professor says that from now onwards, this is the talk which he gave in 2011. You can see it here. Future information technology era ends around 20 to 30. That means even we have fortune to work for another 10-40 years, but he says that most of the research will be in molecular communication. You believe me? I agree to this point. Most of the papers which I kept exploring, people are trying into this molecular. Very less people are trying to work on this. Maybe once you go to 6G using terahertz band, that's possible. Okay, till now we were sitting in 2010. Now let us come back to 2021. So if you are listening to a sci-fi story, no please. So these are some of the links which I have collected. You can have a look at these links where it will show about the present scenario. All this is not your sci-fi story, it is the reality. And this is some of the proposed model for future military applications. So I collected some links for antennas, batteries, memories and all. So 1 minute. Please remember, this is not your perfume or anything else. This is a spray-on antenna system. Just I was going through this link. You just read one of this link here to understand its story. Okay, so I'm done with my presentation. Sorry, I have taken 10 minutes extra, and in between I have to rush some of the slides. So I thank all the authors who made these resources available for me so that I was able to make this presentation, and actually we are trying to work on this. So thank you one and all. If you have any questions, I'm ready to take up those questions. And there's one more number from Tesla's, it is 9, and I have these two statements for you. So why I have mentioned this, see, he was playing with these numbers 3, 6 and 9. That has nothing to do with my research. Fortunately, there were 3 points which I showed in the second slide. 6 research papers I got. Total number of slides I have 108, which turns out to be 9. Yes, Tesla's numbers are magic. And then on the right hand side, we have something for us. He's asking us to explore in terms of frequency, energy and vibration. So that is what, if you try to understand the language in terms of frequency, your communication aspect will be done. And then the other research which people are exploring at present is network layer, transport layer, and application layer. Don't know when it will start. Okay, I'm done with this. Thank you. So any questions?